Hello sir, good evening sir.
Yeah, good evening, very good evening. So, welcome to week 6 discussion of this course, Computer Vision. And this course is taken by Professor Jayanta Mukhopadhyay, Professor of Computer Science and Engineering Department, IIT Kharagpur, and myself, Ayan Paul. I am a PMRF research scholar from IIT Kharagpur, and I am the TA of this course. Okay, so by TA, my duties are I will solve a few questions that will be very much similar to your assignment, so that whenever you will solve assignment, you will not feel it's like completely new. Okay, so that are my duty. But before that, what I prefer, I always prefer to I always prefer to solve some of the to discuss some of the theories related to this week, so that it will be better for us for understanding the question. Okay, so with this, let's start the discussion. Okay, so we this week we will discuss something like feature detection. Okay, so what is feature detection? So feature detection, it is, yeah, feature detection, it is to find distinctive and repeatable points region in an image that can be, yeah, that can be reliably identified across different images, even if the object is rotated or scaled or illuminated differently. What does that mean? So feature, every image is consist of some distinct feature. So what is this feature? So feature is nothing but you can say key points or interest points. Okay, so what is this feature detection? It is to find distinctive and repeatable points. Okay, distinctive and repeatable. Whenever we are talking about features, so those points are distinctive but repeatable. Okay, repeatable, it can be points, it can also be region in an image that can be reliably identified across different images. Okay, so what are the desirable properties of detected feature? First is repeatability, I have already told. Second, distinctiveness, I have again discussed. Third is invariance, that is very important. Invariance means even if the object or the image, object means our object is nothing but the image, even if our image is rotated, scale, or illuminated differently, then also it is robust to that. So that is very important for this feature. Okay, and third is locality, that is localized to avoid occlusion changes. Okay, so these are the four different features of four different, you can say, characteristics of the features. Okay, so you can see this three image that you must have already seen in your lecture. So this three image, it distinguish between a flat region, an edge, or a corner. So what is the difference? Like whenever you are talking about any flat regions, okay, flat region means there will be no change no change in directions. Okay, no change in direction. Even if you can see this is a green window. Okay, if this green window can be moved in a flat region, there will be no change in directions. Okay, even if you will move this green window in x towards x or towards y, there will be no considerable change in directions. Okay, so this is that is why this reason is flat reason. Second, if we talk about edges, this second is whenever we are moving this green window over the edges, what we will see is there will be change in direction along certain direction. Like y direction there will be change, but x direction there will be no change. So that is why this is edge. Okay, there will be changes in a particular direction, that is y direction, but x direction will be no change. So that is why this is known as edge. But whenever we are talking about corners, even if you will shift your window in this x direction or y direction, there will always be changes. So that is why it is corner. Okay, so flat region, no changes in all direction. Edge means no change along one direction but significant change in another direction. Corner, significant changes in both the directions. Okay, so that is how we distinguish between flat region, edge, or corner. Okay, so this corner is one of the most important feature, because corner, whenever we are just moving our window along any direction, there will be suitable changes. So that is why this corner is one of the most significant, you can say most significant feature along an image. Okay, so this is mathematically it has been shown here. So mathematically you can see SSD, that means sum of squared error. So sum of squared error can be find out. So this xy is our original point, but u and v is significant change. Okay, along u is significant change along x direction, v is significant change along y direction. Okay, so if we do the squared sum error, this is nothing but squared sum error. That means intensity along the new point, that is x plus mu, x plus u, and y plus v, and this is intensity along the old point, that is xy. So this square error can be calculated like this, that is sigma x comma y. That means over the whole window, if we take xy, like xy can be many points, x1 y1 x2 y2, like that over the whole window. Okay, so intensity of the new point minus intensity of the old point and the squared of it. Okay, so that is sum of squared error. Okay, so that can be find out like this, but this can be mathematically also simplified like this. Okay, so here you can see uv, that is the vector of the previous point, and then we have, this is actually written in matrix form. Okay, so uv is the row vector, uv is the row vector, and h is your this matrix is known as this matrix is known as this matrix is known as this structure tensor. Okay, structure tensor H. Okay, so structured tensor, how it is made, or the second movement matrix. Okay, these are the two names, second movement matrix or the squared tensor. Okay, so what is squared tensor? That is the intensity. Ix is nothing but change in intensity along x direction. Ixy, this cross change in intensity along the point. Y is change in intensity along the y direction. So this is the H matrix, and U and V is nothing but another column matrix. Okay, so this is nothing but your eigenvalue decomposition. Okay, that you can also write it like this, eigenvalue decomposition. So eigenvalue decomposition, you know, this EUV, but nothing but that will be some kind of matrix. Okay, so this matrix can be solved like this, that is eigenvalue decomposition. So eigenvalue decomposition, that this is your matrix H. Okay, and this is your this is your row matrix, and this is your column matrix or column vector, row vector or row matrix, and this is your column vector or column matrix. But this is the most important matrix out of all these three. Okay, why it is important? Suppose the center of this green window moved anywhere on the blue line. Okay, blue line or whatever line, this black line, direction of the largest and smallest e value, that is eigen vectors of H. Okay, so eigenvector of H will imply, eigenvector will have two things. One is direction and one is the scale associated with it. The scale means how much is the change is having, and direction means in which direction the change is happening. So these are the two things that this H matrix will signify us. So H matrix is the most important matrix out of this. Now this is a quick eigen okay, so this is a quick eigenvector review. So eigenvector is nothing but this H any H into this vector x. Okay, H into x will be equal to lambda into x. Okay, so H is nothing but your structure tensor vector, or structure tensor matrix, that is H. X is nothing but direction associated with this structure tensor, and lambda is the eigenvalue or the scale related to your H matrix or your this structure tensor matrix, and x is nothing but your direction related to your structure tensor matrix. Okay, so that is regarding quick eigenvector review. Okay, so this is regarding eigenvector and eigenvalue review. Now the thing is how we will calculate it is very easy. How you can calculate it? Your eigenvalue can be calculated like this, can be taken in this direction. So h minus in previous class also we have discussed, but here also it is better to discuss. H minus lambda, okay, H minus lambda, this is lambda, okay, H minus lambda into x will be equal to 0. So that means if we just do the mod of it, this x cannot be 0 because this is a vector or direction associated with it, but this will be 0 if we just mod it. So H minus lambda mod will be equal to 0. Okay, H minus lambda mod will be equal to 0. So by this you can find the lambda or the eigenvalues associated to your structure tensor matrix. Okay, so again this is the same written, that is I have already told you, you will get 2 eigenvalue, because if the structure tensor is of as you can see, the structure tensor is nothing but a 2 cross 2 matrix. Okay, 2 cross 2 matrix. So 2 cross 2 matrix means you will get 2 eigenvalues. Okay, so one eigenvalue will be eigenvalue in one direction or the largest increase. Okay, so you will have get 2 eigenvalue, one will be greater, one will be less. Okay, so greater eigenvalue we denote it as lambda plus, smaller eigenvalue we denote it as lambda minus. Okay, so x plus is the direction associated with the with the larger eigenvalue, and x minus is the direction associated with the smallest eigenvalue. Okay, so this is the thing regarding your decomposition of your H matrix into eigenvalue, respective eigenvalue. Okay, so this is how you do it. For a local image, you will first find the structure tensor. Okay, once you get the structure tensor, you can get the eigenvalue related to structure tensor, that is lambda plus and lambda minus. Now how you can know these 3 cases? We have discussed regarding these 3 cases. One, flat region, second edge, and third is corner. So if both your eigenvalues are very small or very closer to 0, then there is no significant change. No significant change means it is a flat region. If one eigenvalue is large, okay, one eigenvalue is large or greater than 0, and the other eigenvalue is lesser than other eigenvalue is significantly less. Okay, now how much less, that will be dependent on the threshold, but you can easily compare that one eigenvalue is very much greater than 0, other will be close to 0. Okay, so in that case what will happen is you will consider this structure or this feature as your edge. Okay, and how you can say it is corner. It is corner if both your eigenvalues are large. Okay, so that is corner. Okay, so we can discuss it by this example 1 or exercise 1, whatever you are tell. So given the structure tensor, we are already given with the structure tensor. Okay, so which of the following best describe the reason? So very easy. How we will do? First we will find out the eigenvalue related to h. Okay, so very easy. Same, h minus lambda I. Okay, h minus lambda won't be anything, but whenever we are this h is matrix, so lambda is a scalar, so just we cannot subtract a scalar from a matrix. Then what we do, that is why we multiply it by I. So h minus lambda I mod will be equal to 0. Okay, so I is nothing but your identity matrix, that is 1 0 0 1 in case of 2 cross 2. Okay, so that means your h minus lambda will be equal to 5 minus lambda, 2 and 3 minus lambda, and then just do the determinant or take the determinant of it and you will get the lambda. So this is the solution. So just determinant of h lambda, 5 minus lambda into 3 minus lambda minus 4. So that will be your equation, and that characteristic, this will be your equation, and this equation is also known as characteristic equation. Okay, and this characteristic equation should be equal to 0 to get the eigenvalues. So we are getting 2 eigenvalues. One is 6.236, another is 1.764. Okay, so we have got this 2 eigenvalues. Now both these eigenvalues are large. Both these eigenvalues are not large. You can see there is a significant difference. Lambda 1 is 6.236. Okay, but lambda 2 is small. Lambda 2 is small, that is 1.764. That means there is a significant difference. As there is a significant difference, then our case will be second. That is the that is, it describes this H matrix describes a H. Okay, if both is close to like 6 or 6, then we can say it is a corner. Okay, if both is very closer to 0 or both like 1, then we can call it a flat region. Okay, so that is the interpretation by an example problem. So is this problem clear to all of you? Any doubt in this problem? Is it clear?
Sir, can you?
Yeah, please.
Yeah, here two eigenvalues we are
Yeah,
determined, right? So lambda one equal to approximately 6.2 and
yeah,
lambda equal to 1.76.
yeah, yeah.
So it's nothing but lambda eigenvalues are one value is greater than zero and another is approximately zero, right? So in that case only we have to consider edge, right? But here not approximately zero, second value.
Yeah, not approximately 0, that is not means flat region means the lambda values are very closer to each other. Okay, lambda values are very closer to each other, that means no significant change, that is flat region. Second case, H, one lambda value will be large and there will be very close to 0 or like 1 is okay. Okay, means closer to 0, closer towards 0. Once one will be significantly large, other will be small, so that is H. Third is corner, that means both lambda values will be higher or higher, or you can say, if here like in this example, if both is closer to like 6 will come, then we can say it is a corner point. As one is coming 6 and another one is coming 1, that means 6 times one lambda 1 is actually 6 times, or you can say 1.7, that means 4 times, 4 or 5 times of lambda 2. So so your first lambda value is significantly large than your second lambda value, so that is why it is an H. Okay.
No, sir. It's 1.7, right? 1.7 we should not consider approximately zero, right? It's 0.0, 0.0 or 0.0123 4 like that. If we get value like that, we have to consider approximately zero. Otherwise, it's 1 point is there, right? It's approximately 2. 1.76 means approximately 2, right? Second value.
Yes, yes,
Eigen,
yes.
second eigen. So we have to consider it's
No,
not zero.
no,
We should
not
not
0. You don't confuse with 0. If both are same, then flat region. Okay. If both are same and closer to 0, closer to 0 does not mean 0. Okay, closer to 0, then it is a flat region. If one is large and the one is small, then it is a H. Okay. And third
uh,
is if
okay,
both.
it's okay. Can you see in the step two?
Yeah, step 2 it has been written like that, but actually that it signifies. Okay, it is
Okay,
not like 0. Okay.
okay, okay.
Okay, you can see in that image, let me show you again. You can see over here. Okay, this image, it will be very clear. Okay, if you move this green region, if you move this green region around this flat region, then there will be no, there will be very less change in the lambda values, right? So that is why flat region. If you will move this in one direction, then like y direction, then you will have more change. X direction, we will have less change. Whereas here, if you can move in both the direction, there will be significantly more change. So that is why this is third one is corner, second one is H, and first is a flat region. Okay, so that it signifies it. Okay, is it clear?
Yes, sir.
Okay, so that is the thing. Okay, so yeah, so this is the thing. Okay, so this is regarding example 1. So any type of question, if it will come in your assignment, you can do it like this. Okay, then feature detection algorithm. Okay, feature detection algorithm, we just have discussed that compute the gradient each point in the image. Okay, obtain the H matrix, you have to obtain this H matrix, compute the eigenvalue, and then locate the point with large response, that is lambda minus greater than threshold. Okay, select point where lambda minus is a local maxima as feature. Okay, so what this means is Meaning of lambda minus as maximum. What does that mean? So at an edge, lambda plus is large, lambda minus is small. Okay, that is so lambda minus not useful feature here. But at corner, that is why corner is the most important feature. At corner, both the eigenvalues are large. Lambda minus also takes a large value. Okay, thus lambda minus is maximal, has a strong response in the image. It means we have found a corner like structure, a true feature point. So that is why corner point is the true feature point, and lambda minus is considered as a local maxima. Okay, so lambda minus is actually it is known as a true feature point. So that is local maxima indicates. Okay, so lambda minus is actually the most important eigenvalue out of lambda plus and lambda minus. Okay, so in other words, edges only give strong eigen values that in one direction, that is lambda plus. Corner in both the direction, lambda plus as well as lambda minus. So maxima in lambda minus indicates stable feature point, corners instead of edges. Okay, so that it signifies this. So that is why lambda minus is the most important eigenvalue out of the two. Okay, so lambda minus should be significantly large to call it a corner point or a true feature point that we are interested in. So one is you can simply find the feature by this eigenvalue. Second, we have a operator known as Harris operator. Harris operator is nothing but it only take care of this lambda minus, but it has this formula. Okay, f is given by this lambda 1 into lambda 2 divided by lambda 1 plus lambda 2. So lambda 1 lambda 2 is the determinant of h, and lambda 1 plus lambda 2 is known as trace of h. Okay, the trace is the sum of the diagonals of the, you can say, diagonals of the eigenvalues. Okay, this h, okay, I will show you how to calculate. So very similar to lambda minus but less expensive, called the Harris corner detector or Harris operator. Lots of other detector. This one is the most popular. Okay, so simple, lambda minus, as it is our most important feature or the most important eigenvalue to get the know the corner feature. So that is why lambda minus is also given by a different operator known as this Harris operator. F, or this f is known as nothing but the Harris operator, that is lambda 1 into lambda 2 by lambda 1 plus lambda 2. So how this Harris operator is calculated? So this is a structured tensor, you can see H4113. Okay, now we have to calculate the Harris operator. So very simple, Harris operator is given by this formula, lambda 1 lambda 2 by lambda 1 plus lambda 2. So very easy. First, this is our structure tensor. What we will do, we will find out the characteristics equation, that is h minus lambda I, determinant of it will be equal to 0. So 4 minus lambda into 3 minus lambda minus 1 will be equal to 0. So 4 minus lambda into 3 minus lambda, that is will be equal to lambda square minus 7 lambda plus 12, and minus 1, that is why plus 11. So this is our characteristic equation. So as we get the characteristics equation, we have to find this, that is f. So f is nothing but lambda 1 into lambda 2 by lambda 1 plus lambda 2. That is the f operator given. Okay, so f operator, how f operator can be found? Lambda 1 into lambda 2. So lambda 1 into lambda 2. So if we see this equation or our characteristic equation, the multiplication of two roots will be given by c by a. So multiplication will be 11 by 1. Okay, so that is why lambda 1 into lambda 2 will be 11 by 1, and lambda 1 plus lambda 2 will be minus b by a. So minus of minus 7, that will be equal to plus 7 by 1. So 11 by 7 will be equal to 1.571. So our Harris operator, or the value of Harris operator, is 1.571. Okay, so is this thing clear, how we get the lambda 1 into lambda 2 and lambda 1 plus lambda 2? Is this thing clear by the equation?
Yes, sir.
Clear, right? Lambda 1 into lambda 2 will be equal to c by a, and lambda 1 plus lambda 2 will be equal to minus b by a. If our characteristics equation is ax square plus bx plus c equals to 0. Okay, so easily you can find lambda 1 into lambda 2. Even you can calculate lambda 1 separately, lambda 2 separately, but to simplify it, always if quotient comes with Harris operator, very easily you can find this lambda 1 into lambda 2 and lambda 1 plus lambda 2. Okay, so that is how you can calculate the Harris operator. Okay, so this is the thing. Now let's move on to the feature description and matching. So in the first slide, what we have seen regarding feature detection. Now we will see about feature description and feature mapping. What is this feature description? So it represents the local neighborhood around each detected feature. Feature detection means we are detecting only the feature, but in description we represent the local neighborhood around each feature in a way that is distinctive and invariant. Okay, so feature detection means we are only pinpointing a certain feature. Okay, we are not seeing the neighborhood around it, but feature description we are interested in the local neighborhood, again in a way that is distinctive and invariant, so that feature from different image can be compared or matched. So this feature descriptor is actually used in feature mapping. So if you are just doing the feature detection, so actually you cannot match the two scene. If you are given two scene, that is rotated, scaled, translated, etc., means two images that are rotated, scaled and transformed. If in first image you are asked this is the x1, let's x1 be the feature in the first image, so can you find the same feature in your second image or not? So if you just know the feature in this image, so you cannot find out the feature in that image, because it is very easy, because of spatial transformation like rotation, scaling, transformation, you cannot find out that feature in that image. Okay, you even if actually you cannot find out the feature in the second image. So that is why it is important, the feature that you are detecting, not only that feature is important, but the local neighborhood around that feature is important. Okay, so that is done by done by our feature descriptor. Okay, so it represents the local neighborhood around each detected feature in a way that is distinctive as well as invariant. Two things are important: distinctive as well as it should be invariant. Okay, so descriptor properties: rotation invariance, I have already told you, should be rotation invariance. Scale invariance, that means whatever scales or how much zooming in or zooming out that has been done, then also we can easily it is invariant in the first as well as the second image. And third is robustness, it works under noises, blur, illumination changes, etc. So these are the three properties of the feature descriptor. Feature matching: after feature detection and feature descriptor, we come out with feature matching. Feature matching matching is the process of finding corresponding feature between the two or more image. Okay, so feature matching, how feature matching is done: first we do the feature detection, that is find the key point in the image. Okay, then we do the feature description, that is local neighborhood, not only the feature detection point, but also the neighborhood around it by our feature description. And once we do the feature detection and feature description, we have to do the feature matching, that is compare descriptor to find the correspondence. Okay, so that is feature matching process. So first feature detection, then feature description, and then after feature detection and feature description, we can finally do the feature matching, that is the process of finding corresponding features between the two image. Okay, so that is the feature matching. So idea of scale invariant detection. Okay, so scale and there should be scale invariant detection, that is scale invariant detection is very important. That means the key point should be scale invariant. So for that, to have the scale invariant detection, find the scale that gives a local maximum of f. Okay, local maximum is important. So f is a local maximum in both the position and scale. That means in both the images, f should be your local maximum in position as well as the scale. If we can do that, then we can easily say that this feature is scale invariant. Okay, so that we do by Laplacian or difference of two Gaussian, that is log or this GOF. Okay, so we will see log or dog. Okay, log or dog, that means Laplacian and the difference of Gaussian, that we will discuss. Okay, So detection and description both should be invariant. Okay, so how we can ensure detector to be transformational invariant? Harris measured the invariant to translation and rotation. Okay, so by Harris operator only, this detector is invariant to translation as well as rotation, but we are missing scale, because this three things it should be invariant: translation, rotation, as well as scale. So by Harris operator only it is invariant to translation and rotation, but not scale. Okay, so scale require handling of multi-resolution representation. That means if we zoom in and zoom out the image also, that this feature should be same. So usual approach computing, yeah, we will discuss by what we can do. We can do the scaling by this method. Okay, that is Laplacian or the dog, that is difference of Gaussian. And second is feature descriptor should also be invariant. So it captures the information in a region around the detected feature point. Not only feature, but also the local region around the feature. That is also important. So that should also be invariant, transformational invariant. So example, historian gradient in a square window centering the feature point. So historian gradient means the local region around the feature that will have some intensity. Okay, so that intensity, if we can get it with by a histogram, and that intensity if we can show it is same in both the images, so by that we can do the feature description. Okay, so this is the thing. Now this is a scale invariant detection. Yeah, so two things I have told you for scaling. One is Laplacian. This is how we do the Laplacian scaling, and this is how we do the difference in Gaussian scaling. XY is the point and sigma is nothing but your standard deviation. Okay, so by this we can change our image point into this L, that is Laplacian, and this by this we can change our image point into dog or difference of Gaussian. So why we are changing it? Because both the kernels are invariant to scale as well as rotation. Okay, we have to scale is the most important, because even Harris operator is invariant to scale and rotation. Okay, but not scale and rotation, translation and rotation. Okay, Harris operator is invariant to translation and rotation, but to make it invariant to scale, we have to convert it into Laplacian or the difference of Gaussian. Okay, so these are the formula. We can this is the relationship that is not very important to us, but yeah, this is the thing. Okay, how we can solve the how we can get the Gaussian operator of an image, and how we can get this difference of Gaussian operator of an image point. So consider a Gaussian with sigma equals to 1. Sigma is nothing but standard deviation of your Gaussian function. Okay, so each image point will form some Gaussian, each image point, or you can say intensity of image point, will form a Gaussian distribution. Okay, so that Gaussian distribution will have some intensity, that is will have some standard deviation, that is sigma equals to 1, that has been given in this question. And this formula is also given, this formula is also given, that is gxx will be equal to, this is not 0 0, but this should be xy sigma will be equal to 1 by 2 pi sigma square e to the power minus x square plus y square by 2 sigma square. So that is how we can get the Gaussian kernel of this image point. Okay, so at point 0 0 we have to calculate. So very easy, just put x equals to 0 and y equals to 0 in this formula, and sigma equals to 1, because it is given. You can get the Gaussian of it. Okay, Gaussian kernel of this image point, that is 0.1592 it is coming. Now here it has been told at point x equals to 0, y equals to 0, and sigma equals to 1, and for this difference of Gaussian we want another thing, that is k. Okay, k is nothing but a constant. Okay, so k also we require, so k is also given, that is 2. Again formula we know, this is the formula we know. So first what we will do, we will find this, that is we will find this we have already find gxy sigma. Okay, gxy sigma 0 0 1, yeah, this we have already find. Now we have to find gxy k sigma. What is k? 2. Okay, so 2 into sigma equals to 1. So gxy comma 2 we have to find. Okay, xy is 0 0, so g 0 0 2 we have to find, g 0 0 1 we already find, and then we can do the dog, that is difference of Gaussian, that will be equal to g 0 0 2 minus z 0 0 1. Okay, so this is the step. 0 0 1 we have already find in the previous question only. Okay, and g 0 0 2 we can find out. 0 0 2 means here the sigma value will be 2 here. Okay, so 1 by 2 by 2 square, and as x y both are 0, then this thing you it is not required to do. Okay, so this is the thing. So G002 also we have found out. Okay, that is 0.0398 coming. Okay, so 0.0938 minus 0.1592, whenever you will do, you can get the dog dog kernel. Okay, that is minus 0.1194. Okay, so is this question clear to all of you? How to get the Gaussian and how to get the dog? Clear, right? Is it clear? Yeah, I think it is clear. Okay, so moving on. So this is the finding key point. So again, should be clear by this. So scale invariant detector requirement. What is the requirement of it? Okay, so what is the actually requirement of scale invariant detector? So if we just run a corner detector like Harris or a blob detector, blob is nothing but this can be a blob like, if I just do this is a blob. This is blob means in this patch you can see the intensity is dark, and out of this patch the intensity is very bright. So this type of structure is known as blob. Okay, that means a structure in which the intensity in it is constant, but whenever the intensity out of it will be very different. Okay, so that is blob. So if we just run a Harris detector, corner detector, you have just seen Harris detector, or a blob detector at fixed scale, it will only find feature at that scale. Okay, a corner in a zoomed out image may vanish when zoomed in. Okay, so like this corner, or like even this picture, if this is very small and we just zoom in, okay, this actually will get vanish. Okay, so we need scale invariant detection for that feature that are found reliable even when image are resized. Okay, so that is what we need for our scale invariant detector. So again I am repeating, what is the problem with this corner detector or even blob detector? At a fixed scale it will only find feature at that scale, but if we just modify the scale, means if we just zoom in, okay, if we just zoom in the image, okay, so that corner might get vanished or this blob might get vanished. So to deal with it, we have to do the scale invariant detector. So how we do the scale invariant detector? We apply this theory, scale space theory. So what is the scale space theory? So in space to localize where the feature in this image. So this can be done like the Harris detector, etc. And then we have to do the scaling to localize at what scale the feature is strongest. Okay, so that we have to find out. So for that we can do this. We can apply this scale space theory. Okay, this is scale space theory. Why it is scale space theory? Because whenever we are doing this g of x y sigma into this image point, so we are actually scaling the image. Okay, this can be seen from this diagram. You can see this is our original image. The block at the block or the surface at the lowest point. This surface is actually our normal image. Okay, then what we are doing, we are just scaling the image. Okay, that means we are just scaling the image, or you can say we are just doing the g operation. Okay, g x y operation, that means Gaussian operation, that means we are just blurring the image. Okay, so this is actually blurring, so we are just blurring the image step by step. Okay, and then we are finding the dog. Okay, this is the dog operator. And second thing is we are also scaling the image. Scaling the image means you can see this size of this this patch, and size of this patch is actually, this patch is half of the size of this patch. So we are again scaling the image. Okay, so two things we are doing, we are putting the Gaussian operator to have effects like blur, etc., and then we are scaling the image. Okay, so this is known as scale space theory. So we are doing the blur and etc. to have the to localize where the feature is in the image, and then we are doing the scaling of it. Okay, so this is how we do it. So we can see it by two operator. One is this Harris-Laplacian operator, Harris-Laplacian detector, and second is the our scale invariant feature transform. Okay, so Harris measure, yeah. So two steps are there. First is to find x, y, and second is for scaling. Okay, that means to find the feature, and second is to scale the feature. So to find the feature, this Harris-Laplacian operator, it uses the Harris operator, okay, to find the feature. And to make it scale invariant, we do the log of it, that is Laplacian of Gaussian. Okay, so that we do for scaling purpose. So that is Harris operator, or yeah, that is Harris-Laplacian operator. Second, we have a special operator known as SIFT, that is scale invariant feature transform. So here also we apply the same theory, space scale theory, but here we apply it in one step. Okay, so here you can see this dog detects both where x and y are there, and what scale sigma in one unified step. Okay, so what is the difference? Harris-Laplacian, we have, okay, someone is joining. Yeah. So Harris operator, we are finding Harris-Laplacian operator consists of two steps. Okay, first step we find we localize the feature, that is we find the feature by our Harris operator. Okay, Harris operator to find the feature, and then we, for scaling, we apply the Laplacian. But scale invariant feature transform, in this operator we are only doing the dog. No need to find the Harris operator, but we are only doing the dog. This dog takes care of both, to find the feature, that is to it find both x, y, as well as it also do the scaling. Okay, so this scale invariant feature transform is a one-step process, but this Harris operator is a two-step process. So that is the difference. So Harris-Laplacian, it is a two-step process that I have told. Harris for location, Laplacian for scale. Okay, so it is good for corners. SIFT, it is more general. It only by dog only, we dog or difference of Gaussian only, we find both location and scale. It is more general, find blobs as well as corner. Okay, so this is the difference between both the operator. After this, we have this something called SURF. Okay, speed up robust feature, SURF. Okay, this is actually, you can say, extended version or extended form of your SIFT operator. Okay, so here also we are operating the feature as well as location by your dog operator only. But here what has been done, this dog operator, so let me show you this. Yeah, core feature here, what has been done, when we are finding the second order derivative of the Gaussian function or the Laplacian of it, we are applying a box filter. Okay, why we are applying a box filter? To simplify the calculation. So this is our Hessian matrix. Okay, LXX, LXY, and LYY. We can see by the subsequent example how to find it. But this is the Hessian matrix. Okay, so after this Hessian matrix is this L is nothing but your Laplacian. Okay, so this is the thing. But here what this SURF operator do, this SURF operator actually what it do is it approximate the process by use of box filter. So your complex calculation will be your H, we do not calculate the exact H or the exact Hessian matrix, but what we do the approx calculation by changing the LXX to something called as DXX. Okay, that is the approximation of it. So DXX is nothing but, you can say, some approximation of your LXS, as well as similarly DXY is C of LXY, similarly DYY is nothing but C of Ly by. So we are just approximating it. Okay, so by doing it, what we are doing, we are actually enhancing our calculation. Okay, so and this is the first feature of our surf operator. Okay, so this is the first feature. Second, we have something called wavelet. So after detecting the key point by this surf, orientation assignment we have to do, and then descriptor construction we have to do. So orientation assignment we do by Har responses. So Har responses is nothing, this dx dy. Similarly, there will be for reconstruction we have this another thing, that is absolute value of dx and absolute value of dy. So how dx is calculated? That is the intensity of a point ahead of our actual point in x direction, minus intensity of point behind our actual point in x direction, that is the dx. Similarly, similarly this dy is intensity of x y plus 1. That means intensity of a point above of our actual point, and intensity of point below of our actual point. Okay, so that is how we calculate the Har wavelength responses, and we can get the mod del x and mod del y. Okay, and by this we will have, for each point we will have 4 responses. Okay, so actually what we do is take a square region around the key point. First we detect the key point. Okay, and then what does Har wavelet do? Detect the key point is done by this step. Okay, by getting the Hessian matrix and do the box filter of it. By this, what we do, we just found a feature point, that is the corner point or blob point, whatever the points. Okay, and then descriptor construction, how we do the then there is this orientation assignment we do by Har wavelet response, that is to find the del x and del x or dx or dy. And then what we do for each key point, take a square region around the key point. So we have detected the key point, then we take a square regions for like 4 cross 4 sub region you take, and what you do is for each point, for each sub region, or for each sub region you will get this 4 things. Okay, that is this del x and del y is not for point but for sub region, because sigma is also there. That means for each point, in that region, for each point, if we just sum up all the responses, we can get the sigma of it. Okay, so for each sub region we compute the Har responses of x and y. So we will have 4 values, del x, del y, and mod of del x and mod of del y. Okay, and after that what we can do, we can 4 into 4 region, and we have 4 responses. So total for each sub region we will have 64 dimensions. So that's why that's how Har wavelet that's how we can do the descriptor construction. Okay, so if we just sum up the difference of this SIFT and SURF, because SURF is nothing but an extended version of your SIFT. Okay, so detector, there it is a dog, here it is a Hessian matrix, but approximation of it. Okay, that is very important, approximation by box filter. And then there we have this 128 descriptor, but here we have 64 descriptor. You can see there we have 64 descriptors. So that is why actually your surf is very fast, 3 to 4x fast. First we have less descriptor, and second thing is this Hessian matrix is actually approximated. So that is why this surf is actually 3 to 4 times faster than our SIFT. But if we talk about robustness, because SIFT operator we are doing the actual calculation, we are not doing any approximation, so it is more robust. But SURF, it is approximately robust, but it is actually less robust than SIFT. Okay, so that is the difference. So what we have discussed, we have discussed 3 things. Okay, first is this Harris-Laplacian, then SIFT, and then SURF. Okay, so Harris-Laplacian, we are doing the 2 things we have to do. First we have to find the detector, and then we have to scale it. So scaling we are doing by Laplacian, and finding we are doing by Harris. Okay, Harris operator. SIFT we are doing both the thing by dog operator. There we are doing the thing by both the thing by by our Hessian matrix, but approximation of it by using the box filter. Okay, so that is the difference. Also, if I compare specifically because between SIFT and SURF is actually faster, because SURF we are doing approximation and we have less descriptor point. Okay, so that is why SURF is more faster than your SIFT. Okay, but it is actually less robust. No, we cannot say it is very less robust, but it is approximately less robust than SIFT. Okay, so that is the difference between SIFT and SURF. Okay, so this is the thing. Okay. Okay, sorry, I got logged out of it. Okay, let me go again. Yeah, is my screen visible?
Yes, sir. Visible, sir.
Yeah. So that is the tree descriptor. Okay, that is the tree descriptor, but these three are key point descriptor. Okay, so these are the three difference between the key point descriptor. One is Harris-Laplacian, second is your SIFT, and third is your SURF. Okay, so this are the difference between Harris-Laplacian, SIFT, and SURF that you have to remember to solve your question. Okay. Then we have a question regarding this Hessian matrix. So we have been given, this is a 4x4 grayscale image patch, you can see okay, so let me open this. Yeah, so this is a thing for the pixel 2,2 in the above image, the Hessian matrix. What does find out the, actually this is find the Hessian matrix, this will be find here, find the Hessian matrix, and what does that denote? Okay, so that denote, it is very easy. Again, what does it denote? What does it denote? Then again we will do that same process, that is to find out the eigen value of it, and then we can say it is a coordinate or flatesian, etc. So this is actually not important, but it is important how to find out the Hessian matrix. So this H is given by this Ixs, Ixy, Iyz, and Iyy. So how to find this Ixs? Ixs is nothing but del 2I by del x square of x. Okay, similarly Iyy is nothing but del 2Iy by del y square. And then we have Ixy is del 2I by del x del y. That means differentiation we have to do 2 times. Okay, first differentiation will give us the difference in intensity denoted by Ix and Iy, and second differentiation, when we will do the second differentiation, we can get Ixx, Ixy. Okay, so Ix, it is given by this formula, and Iy, it is given by this formula. We have already discussed. So Ix, that is intensity of x plus 1 point, that is point ahead of your point ahead of your target point. Target point is 2, 2. So x plus 1 means your x plus 1 y means your point will be 3, 2, and x minus 1, y means your point will be 1, 2. Similarly, x y plus 1, your point will be 2, 3. X y minus 1, your point will be 2, 1. Okay, so by this we can get the Ix and Iy values. So we got the Ix and Iy values. Now, but in Hessian matrix we have to get Ixx, Ixy, Iyz, and Iyy. For this you have to apply this formula. That means Ixx is nothing but Ix plus 1 x minus 2 Ixy plus x minus 1 y. Okay, so that by that you can get Ixx. Similarly, Iyy, Ixy plus 1 minus 2I yy or xy plus Ixy minus 1. So that by that you can get Iy. Similarly, you can get Ixy. That you have to remember, that will be given by I33. That means Ix plus 1 y plus 1 minus Ix plus 1 y minus 1 minus Ix minus 1 y plus 1 and plus X minus 1 y minus 1 divided by 4. So once you got this, you got the matrix. Okay, that is the you got the matrix, that is this thing, that is the Hessian matrix you got. Once you got the Hessian matrix, Same thing, again you have to do the h minus lambda, you have to find 2 lambda. One is, again you can see one lambda is large and there is like very small, so you can say this is a edge like point, okay, edge like structure. Okay, one lambda is very large, that is in positive 2, and one lambda is and another direction it is negative of minus 4.3. So that is why the point is nothing but a edge like structure. Okay, so important thing is to get the step 1 and step 2. Okay, the step 1 is actually we do not require. Even if you get the step 2, even if you remember the step 2, you can do get the Hessian matrix. Okay, so this thing you have to remember. So is it clear to all of you how to get the Hessian matrix? Is this thing clear to all of you?
Sir, in step 1,
Yeah,
Ix, right? Ix and Iy.
yeah,
So we have 3 comma 2, right? So
yeah.
how we are considering 3 comma 2?
3 comma 2. What is 3 comma 2, right? 3
Yeah,
comma
yeah.
2. Yeah, yeah. So let me show you. Yeah, 3 comma 2. What is 2 comma 2? 2 comma 2 is second row, second column. Okay, this is 2 comma 2. Now 3 comma 2. 3 comma 2 means third row, second column. That is 18. So that 18 is written. Okay, and then what is, we have 1 comma 2. 1 comma 2 is 1 first row, second. That means 10. Okay, now you got it
Yes, sir.
from the image.
Yes,
From
sir.
the actual image, grayscale image, the matrix that has been given, from there you have to get this 3 comma 2, 2 comma 2. 2 comma 2 is nothing but 15, 1 comma 2 is 10, and 3 comma 2 is 18. Similarly you can find the other things like 2 comma 3, 2 comma 1. First index means it is the row, okay, second index means it is the column. So 3 comma 2 means third row, second column. Okay, clear, right?
Yes, sir.
Okay, nice. So this is the one question regarding Hessian matrix. Then other type of detector we have, detector and descriptor. So we have this fast, that is feature from accelerated segment test. Okay, that is fast. So it is actually a fast corner detector. Okay, fast is nothing but a fast corner detector. Okay, so how it works: for a candidate pixel P, take a circle 16 pixel around it. A pixel is a corner. If there exists a set of n contiguous picture in the circle that are all are brighter than P plus T, all darker P minus T. If this condition hold, then P is a corner. Okay, so what does this denote? So first you take a candidate pixel like P. Okay, now what you do, you take a threshold T. Okay, now if a pixel would be a corner if all the pixel P plus T pixel are actually brighter than your P pixel, and if all the pixel P minus T pixel, that should be darker than your pixel. Okay, if that condition hold, then this P or your candidate pixel is nothing but your corner pixel. Okay, so that is how fast operates. Okay, so this is an algorithm. So pro, it is extremely fast. We do not require all this Hessian matrix, eigenvalue, etc. Nothing we require. It is very fast. Okay, so it is good for real-time tracking. Cons: no scale invariance, no orientation assignment, just a detector. It is not a descriptor, but it is a detector. So here you will have no scale invariance or no orientation assignment to it. So this is fast. So fast is nothing but one type of fast corner detector. Full form of it: feature from accelerated segment test. So we just find the corner pixel and candidate pixel, and we assign a threshold to it. And if P plus T pixels, okay, all the P plus T pixel, if it is all are brighter, then all are bright, and P minus T pixel all are darker, then this your P pixel is nothing but your corner pixel. Okay, so that is the fast operator. Second, we have something called brief. So brief, it is actually a descriptor. Descriptor, what does descriptor do? You can say it identify the local area around the feature point. Okay, so for that what we do, for each key point take a patch. We just take up a patch. We define a set of point pair pi qi, and that for each point pair we find this bit of I. Okay, bit of I, a bit of I. If your pi lesser than, or intensity of this point pi is lesser than qi, then we will assign 1, otherwise we will assign 0. And then what we will do, we will form a binary string with this descriptor. In LBP I will explain it, but just understand this, we will do this thing. Okay, so your bit will be 1, our bit will be 0. Bit will be 1 if this pi lesser than, or intensity of pi is lesser than intensity of qi, otherwise your bit will be 0. Just understand this, and whenever we are doing this LBP I will give you a question, and it will be more clear. Then we will have another thing called ORB. It is both detector as well as descriptor. Okay, so it is actually a combination of this fast and brief. Okay, fast is a detector and this brief is a descriptor. So if we just add fast plus brief, we get this ORB, that is oriented fast rotated brief. Okay, detection and orientation, it is done by nothing but your fast, and your description we use this brief. Okay, so this is the thing. You can read the theory, I am not discussing the theory much. So other type of descriptor and detector, so apart from our Harris-Laplacian and SIFT, we have this other type of detector and descriptor. Okay, one we have this detector known as fast. Okay, second we have this descriptor known as brief, and third we have ORB, that is a combination of fast detector and this brief descriptor. You just understand this, and then you can read the theory and all. I am not discussing the theory and all in detail because I will be more focused on the questions. Okay, so this is the thing. Here also I have given the difference between this three methods. Okay, fast is a detector, brief is a descriptor, this is the detector and descriptor. You can see this invariance, no scale rotation here, rotation and some scale, and other thing you can see over here. So this slide this slide or this presentation I will give you, and you can read the theory part. Okay, so this is the thing. Second, we have this matching of feature descriptors. Okay, so when we have this feature descriptor from SIFT, SURF and ORB, we need to compare them. Okay, between two images. Okay, the similarity or dissimilarity is measured using this distance norm. Okay, so we will have this three distance norm. One is LP normalization, L1 normalization and L2 normalization. So what is LP normalization is the general form. So what is LP normalization? So F and G are nothing but your key point feature from your two different descriptor. Like that F, let's say F vector is coming from SIFT, G vector is coming from SURF. Okay, so LP norm, how we can calculate this, compare this two descriptor from coming from two different descriptor. We can do by this LP normalization. LP normalization, this is the formula: sigma I equals to 0 to n fi minus gi mod of it power p and whole 1 by p. Okay, so again I am repeating, actually this we should calculate first, that is fi minus gi mod of it to the power p. Okay, and then we have to do the summation from I equals to 0 to I equals to n, because we will have n number of key points. Okay, from the descriptors, and then we will do 1 by p. Okay, so that is LP normalization. L1 normalization is nothing but when p equals to 1. So same formula, you just keep p equals to 1 and your formula will be called as L1 normalization. Similarly, L2 normalization when p equals to 2. So that is how we do the matching of feature descriptor, or we just compare the feature descriptor from different descriptor like SIFT, SURF, etc. Okay, so this is the thing. This is how we compare the different descriptor from compare the different feature from different descriptor. Okay, so this is the thing. Now now the descriptor like this, whatever we have been discussing, like Harris-Laplacian, then SIFT, SURF, ORB, all these are nothing but key point descriptor. That means there we are finding either the corner point or the blob point. These are known as key point descriptor. Now we will focus on reason descriptor. Okay, now we will focus on reason, not just a key point like corner or at say corner or blob, etc., but we will focus on a complete region. So this type of descriptor are known as region descriptor. So region descriptor, a region descriptor is a feature representation that describe a larger area region of an image instead of a single key point. Key point descriptor we have just discussed, describe a small neighborhood around a corner or blob. Region descriptor encodes an information from an entire region ROI, which may be irregularly shaped, a detected object, a segmented part of the image. So point descriptor, it is local finger point of the small patch. Region descriptor, it is signature of a large image region. Okay, so key point descriptor are actually you can say it is a local finger point, means we are focusing on a very small area or a blob, but here we are focusing on a big region. Okay, so that is region descriptor. So types, we have patch descriptor, we have texture descriptor, and we have this image or subimage global descriptor. Okay, these are the types. Now let's discuss something about patch descriptor. One of the patch descriptor that has been discussed in your courses, histogram of gradient or HOG. Okay, so a patch descriptor, it encodes information about the appearance of a patch. Okay, so this is the key idea. It compute the gradient of each pixel, quantizing gradient orientation, describing histogram, and normalizing over the larger block. So these are the steps, you can read it, but this formula is important, how to do the gradient computation. So gradient computation, like Ix I have told you, so in place of Ix, here we use gradient, for gradient we use Gx. Okay, same thing, you either tell it at you either denote it as Ix or Gx, so that will be given by that formula I have already discussed, that is Ix plus 1y, Ix minus 1y, Iy or gy, that can be given by this Ixy plus 1 and minus Ixy minus 1. Okay, so for each gradient, okay, of a particular point, you will have gradient magnitude as well as gradient orientation. So how to find the magnitude? Magnitude is nothing but root over of gx square plus gy square. Orientation is given by this, that is tan inverse gy by gx. Okay, then what we do the orientation, binding, everything, etc. You can just read it. So this is the operator. So patch descriptor, so again I am repeating, patch descriptor, it encodes information about appearance of a patch, a rectangular region of an image. So we are focusing on a patch. Okay, so that is patch descriptor. Then what we do the histogram of oriented gradient. We got the oriented gradient, and then just we do the histogram of it. By that we are doing the description of your patch. Okay, so then we do the histogram of it, that is why it is known as histogram of oriented gradient. First, again I am repeating, first we do the histogram calculation, and then we do the histogram. We do the histogram of oriented gradient. Okay, we do the histogram of oriented gradient. Okay, so this is the operator known as histogram of gradient. Other things you can read, etc. After this class, but this is the whole idea. Okay, I am a bit fast, but actually you can just read all this theory, so you can just read. Second, this is a texture descriptor. Okay, first type of descriptor is over, that is a patch descriptor. Patch descriptor, we have only studied about one patch descriptor, that is histogram of gradient. Texture descriptor, we will talk about different texture descriptor. So what is a texture descriptor? It is a numerical representation that captures the pattern intensity variation in an image region. So in an image region, it captures the pattern or intensity variation. Okay, pattern of intensity variations. Okay, so first one type of texture descriptor is your edge density and direction. Okay, so edge density and direction. What is edge density? Edge density is given by this formula, n edge by n total. Okay, so first you have to take an image, you have to apply this edge detector like Sobel or Canny. We have discussed in the first class only what is a Sobel or Canny detector. You can just see the first presentation and count the number of edge pixels in a region, that is number of edges. Okay, second, divide the total number of pixel in the region, that is n total. So this will be your edge density. Okay, edge density and direction. So we have got edge density. Again, what is the edge density? That is number of edge pixels. Okay, n edge is number of edge pixel, n total is number of total pixels. Okay, So by this we can get the edge density. So what does edge density means? The region as rough or fine grained texture. Okay. What does low edge density means? The region is smooth or uniform. Like example of a rough or fine grained texture, grass, hair, fabric, etc. Okay. Then low edge density region is smooth or in uniform. So smooth or uniform region like sky or painted wall, like that is low edge density. Okay. So by edge density only we can say it is a either it is a high edge density or a low edge density image. Okay. Second, we have this edge direction. What is edge direction? Edge direction is nothing but same thing. That is to find the theta of the to find the angle between your gx or gy. Gx or gy is nothing but the gradient operators. Okay. So gx is nothing but del I by del x. That is nothing. That is this thing same only. This thing only. Okay. Gx gy and theta is nothing but r or tan inverse gy by gx. Same thing. Okay. So same thing. That is orientation of each pixel. Okay. That is given by theta equals to tan inverse gy by gx. Gy is nothing but I by ix. Okay. Same thing. I by ix, that is also called as gy by gx. Okay. So build a histogram orientation. So after this what you can do is build a histogram like you can have seen in your hog operator. Okay. To build a histogram of your oriented gradient computation. Okay. Just build a histogram and then you can do the interpretation. If histogram has a sharp peak, okay, if the formed histogram like from 0 to 180 the angles are coming and you are separating it into n number of bins. Here like here, if for example I have taken 9 bins. Okay. So if a histogram has sharp peak, it is a strong dominant direction like wood grain horizontal. Okay. If histogram is uniform, no dominant orientation like grass or sand. Okay. So this is the orientation. Okay. Example, brick wall, strong horizontal and vertical orientation, fabric and diagonal weave, diagonal peak in orientation histogram. Okay. So this is the thing. You can just read the theory. So institution and textural recognition. Edge density. What does edge density denotes? How busy the texture is. So that edge density denotes. Edge direction tells how organized the texture is. So these are the two institution of edge density and edge direction. Edge density, it gives the roughness. Edge direction, it gives the pattern orientation. So this is our first texture descriptor, edge density and direction. Okay. So this is the first thing. Second texture descriptor is our local binary pattern. This is important in terms of quotients. Okay. Quotients generally come from this local binary pattern. Numerical quotient. So local binary pattern encodes local texture around the pixel by looking at how its neighbor compares to it. Okay. It converts a small neighborhood patch into a binary code that represents the local structure, flat edge, corner, spots, etc. So if the value is very less, then it is a flat region. If the value is very high, then you can say it is a corner. Okay. So by that you can do the interpretation. Okay. So how does it work? So let me show you by an example. It will be more clear to you. So yeah, this is the LBP. Okay. So LBP again, your local binary pattern will be 1 if your PI greater than PC. If your PI lesser than PC, it will be 0. Okay. What is PC? PC is the center pixel around which you are focusing on, like what it has been told, around the pixel by looking on how its neighbor compare it. So you will have target pixel, right? So that is nothing but the target pixel is nothing but your center pixel, and the pixel around it, that is or the neighbors around the pixel, that is given by PI. Okay. So PC is the center pixel and PI is the neighbor pixel around it. It will be more clear by this example. So consider a 3x3 neighborhood with a grayscale pixel. Okay. So this is a matrix of a image. Okay. Now compute the LBP code taking center 140 as reference using BK equals to 1, neighbor greater than equal to center as 0. So same thing, that LBP, the formula of LBP is given. Okay. If your neighbor is greater than center, then assign it as 1, otherwise assign it as 0. Okay. So that is the formula. The top right is the first neighbor, top right is the first neighbor, and the order moves clockwise. Okay, so this is the first neighbor, and then top right, and then this is known as right, and this is known as bottom right. Okay, top right, right, bottom right. Similarly, this is middle, this is top middle, middle, and this is or you can say center. This is top center, center, and bottom center. Similarly, top left, left, and bottom left. That is how we do the nomenclature of your this thing. Okay, and then the top right is, yeah, and then weights are given. Okay, for this whole matrix the weight is given. Okay, the top right is the first neighbor, order moves in clockwise direction. Yeah, order always moves in clockwise direction. That means you have to do like this. Okay, you have to do like this. I will show you what I am telling, and weights are given as 2 to the power 0, 2 to the power 1 to 2 to the power 7 in that order. Okay, so what is the LBV code for this decimal? So how we can find it? Yeah, so your center is already given, that is 140. Okay, then what we will do, we will compare we will compare center with each neighbor. Okay, so how we can compare neighbor? We will start with the top right. Okay, so top right, this pixel we are taking the top right, so this is the top right pixel. Okay, this is the orientation. Let me erase this. Yeah, this is the orientation that I was explaining. Okay, top right, right, bottom right, top center, bottom, top left, left, bottom left. Okay, that is the nomenclature of this matrix. Okay, now how you have to do? You have to always move in clockwise direction. Okay, top right, then bottom right, then bottom left, then top left, and then top. Okay, that is how you have to move. That is clockwise direction. This is the target pixel. C is the target pixel, so you have to move in actually clockwise direction from the top right. So just take the top right. Okay, and you have to see the value of the top right, that is 160, but 160 is greater than 140, so that is why you will assign the bit 1. Okay, similarly you will see the right is 155, again you will assign the value 1. Bottom right is 145, again it is greater, so you will assign 1. Then bottom is 135, that is lesser than 140, so that is why 0. Okay, bottom left again 0, left is 0, top left is 1. Okay, and top is 1. Okay, so that is how you compute the bit. Okay, that is how you compute the bit or the LBP. Now how we can get the LBP value? We can get the LBP value by multiplying it by the weight and then summing it. Okay, so this bit will be multiplied by the weight that is given for this bit, that is 2 to the power 0 is given. Okay, so 2 to the power 0 means 1, so you have to multiply 1 by 1 into 1, so 1 is coming. So contribution is 1 for this bit. Similarly, what is the contribution for this second bit? That is 1 into 2 to the power 1, that means 2. Similarly, third bit 2 to the power 2, so 1 into 2 to the power 2, that is 4. Similarly, you can do the calculation and then just sum it. Okay, just sum it and your answer will come 199. 1 plus 2 plus 4 plus 0 plus 0 plus 0, then 64 plus 128. So your answer is coming 199. So your LBP code is 199. Okay, so that is how we do the find out the LBP code decimal value.
Sir, sorry to interrupting you. I have one doubt in it.
Yeah, please.
Suppose in this problem, in this exercise, center code 140 is given.
Yeah.
So it is very easy to calculate, right? Otherwise, suppose center is not given, how to calculate?
Center is not given means your image matrix is not given.
Image matrix is given, but
Okay.
center we have to assume. Which code we have to assume?
I'm not getting your question. Can you please simplify it? What you are telling?
Here, matrix is given
Yeah,
and code also given 140. Based on that, we are easily calculated, right?
Yes.
LPP code.
Yes.
LPP code, right?
Yes.
But center is not given.
Means which target point is not given, right?
Yeah. Target point
Target point is not given. So target point
yeah.
will always be given, I think. Why it is not given? It should be
So
given.
which code
By
we have
target
to
point only
refer?
you can compare, right? By target point only you can compare the neighbors. Otherwise, how you will compare the neighbor? right? How you can compare pi greater than equal to pc or pi lesser than pc? How you
Yeah.
can how you can say? You cannot say if your target point is not given, and that is what LBP is, right? It compares the target point with all the neighborhood point, right? So target
So
point should always
pixel
be
as
given.
reference, what it means, sir? Center pixel means in the matrix center code we have to consider, right? Center value.
Center pixel is the middle pixel. Like if you have this 3 cross 3 matrix, then second row second column point will be your center pixel. Okay.
Okay. In the assignment question number 4, problem given like that. So I am asking. Code is not given.
Code is not given means this weights are not given.
Sorry,
Weights are not given. What is not given? Center point is not given. Weights are not given. What is not given?
center not given.
Center point is not given. Okay, so
Yes.
you can assume the center point only. Okay,
Sorry. Can you please
you
come
can
again?
assume the center point only if the target point is not given. Okay, someone is telling given, sir. Okay,
Okay.
I will solve
Sup-
the solution and I will give in that content folder. Okay, but
Okay.
after the release of the solution. Okay, before
Okay.
before that I
Please.
cannot give you. So after
Yes, sir.
the release of the solution, I think Thursday I think they release the solution, right? So Thursday I will give the complete solution. Okay, but this is the
Uh,
step you have to follow. If you just understood it, I think you can get the I think you can do the solution. Okay, or solve the
Okay.
question.
Oh, 1 minute, sir. Only 1 hour.
Yes, please.
So this exercise in A matrix, center code 140 is given.
Yes, yes,
140, that is center, right?
yes, yes,
So you may consider 140 as center, right?
yes,
Reference.
yes,
So similarly, in other problems, if center is if code is not given, center value only we have to consider as reference code, right?
yes, yes, yes. Center you can consider as reference if nothing is given. But actually,
And
target point should be given, I think. Someone is telling
oh,
it is given, so let me see in your assignment. If it is not given, then we can assume the center point. Okay, it should be given, I think. Target point should have been given, but if by printing or etc. Mistakes are there, then you can assume the center point only. Okay.
okay.
Okay. So this is the thing. So is this question clear to all of you? Important question to find the LBP value. Is clear? Is it clear to all of you? You can please ask any point, any doubt. You can please ask because this is an important question. Any step, any doubt, you can please ask. No problem. Clear to all of you? Clear, right? So you can solve the assignment question, right? Similar question, if it is given in the assignment, you can solve it, right? Okay, I hope you can solve it. So let's move. Okay, so now the second thing is co-occurrence matrix. This is the third type of your texture, third type of texture descriptor. First type is as density and direction. Second is this local binary pattern, and third we have this co-occurrence matrix. Okay, so co-occurrence matrix describe how often pairs of pixel intensity occur together. Okay, how often the pairs of pixel intensity that occur together in an image given a specific spatial relationship. Okay, it captures the spatial arrangement of the texture, not just intensity values. So not just intensity values, but it also captures the spatial arrangement of the texture. Okay, now just I'm not reading it but just explaining you by this. For example, this is your image matrix. Okay, now you are asked how to get the co-occurrence matrix of C01. That means 01 is your focus point. Now how you can form the co-occurrence matrix? You just write 0 and 1 in the vertical as well as horizontal. Okay, horizontal you can write and vertical also you can write like this. Okay, that means first row index you tell it at 0, second row index you tell it at 1, first column index you tell at 0, second column index you tell at 1. Okay, just write it like that and then compare the 0 0. Where is 0 0 occurring? So 0 0 occurring here, 0 0 occurring here, 0 0 occurring here, 0 0 occurring here. So 4 instances of 0 0 occurring, so that is why 4. Similarly, when is 0 1 occurring, 0 1 0 1 occurring here, 0 1 occurring here, so that is why 2. 1 0 occurring, 1 0 occurring here, 1 0 occurring here, so that is why 2. Then 1 1 occurring, 1 1 occurring here, here, here and here, that is 4 number of. So number of times 0 0 is occurring, 0 1 is occurring, 1 0 is occurring and 1 1 is occurring. So by that you can form the co-occurrence matrix of this relation 0 comma 1. Okay, so that is co-occurrence matrix denote. It describes how often pairs of pixel intensity occur together. Okay, how often the pairs of pixel intensity occurs together, that is co-occurrence matrix. Then we will have nothing but normalized co-occurrence matrix. What is normalized co-occurrence matrix? If we just divide the co-occurrence matrix by total summation of the co-occurrence matrix value. So what is the summation? 4 plus 2, that is 6, 2 plus 4, that is 6, that means 6 plus 6, that is 12. 12 is the sum of elements of the co-occurrence matrix. So just divide the co-occurrence matrix by 12. So 4 by 12, 2 by 12, 2 by 12, 4 by 12. Okay, 4 by 12 is 1 by 3, 2 by 12 is 1 by 6, 2 by 12 is 1 by 6 and 4 by 12 is 1 by 3. Okay, similarly there is something called as symmetric co-occurrence matrix. What is co-occurrence matrix? Co-occurrence matrix is this C0 1. What is CRXY? Okay, CRXY, whatever you can say. What is this symmetric co-occurrence matrix? Symmetric co-occurrence matrix is CRX comma Y and C minus R X comma Y. Okay, what does that denotes is like 0 0 you are finding, again you have to find 0 0. Okay, 0 here you are finding 0 1 in this, right? But here you have to find 1 comma 0. Okay, 1 comma 0, and there 1 0 you are finding, 0 comma 1 you have to find, and then 1 1 you have to find 1 comma 1. Okay, so you have to do nothing but you have to just sum it, like 0 0 it is coming 0 0 and minus of 0 0. So just take like this. Okay, you can again not minus 1 but minus here. Okay, 0 comma plus 1 only, but minus over here. That means if here you are finding 0 0. Okay, so 0 0 is okay, 0 0 we have 4 value of 0 0. Okay, now you just reverse it. Okay, so 0 comma 0, reverse of 0 0 is nothing but 0 comma 0. So here also you are getting 4, there also you are getting 4. So 4 plus 4, now your answer will be 8 here. Similarly here 0 comma 1. So 0 comma 1, okay, that also you will find. And second thing, 1 comma 0 also you will find. So 0 comma 1 is 2 and 1 comma 0 is also 2. So that is why 2 plus 2. Similarly 2 plus 2 here and 1 plus 1 1 and 1 1, that is 4 plus 4 here. So this is your symmetric co-occurrence matrix. Okay, so 4 and 8, 4 4 and 8. Okay, this is your symmetric co-occurrence matrix. Okay, so this is the thing. Now let's just solve a question. Okay, this is this from your this normalized co-occurrence matrix you can get all this properties. Okay, you can find the energy by this formula, entropy by this formula, contrast by this formula, and homogeneity by this formula, and the correlation by this formula. Okay, so this is the thing. Okay, now let me solve one question to have your doubts clear. So this is our given image matrix. Consider the direction 0 1 right neighbor. So just forget it, just you consider 0 1. Okay, now what you have to do, you have to find the co-occurrence matrix. Okay, just find the co-occurrence matrix. So 0 0, where is 0 0 coming? 0 0 coming only at one position. Okay, and 0 1 coming, 0 1 coming at 0 1 coming, 0 1 is coming at 1 and 2 positions, so that is why 2. Then 1 0 coming, 1 0 coming at 1 0 and another 1 0, 2 positions, so that is why 2. And fourth thing is 1 1 coming, 1 1 coming this position, 1 1 coming in only one position, so that is why 1. So this is our co-occurrence matrix. And after co-occurrence matrix it is very easy to find the normalized co-occurrence matrix. What is the sum? 1 plus 2 3, 2 plus 1 3, so 3 plus 3 is 6. So 1 by 6, 2 by 6, 2 by 6 and 1 by 6. So this is your normalized co-occurrence matrix. And then you have to find all the things like energy, entropy, and then contrast, homogeneity, and correlation. So energy that is found by this formula, that is nrxy. Okay. So yeah, this is the thing, 2 into 1 by so nrxy whole square. So nrxy, so that means this matrix you have to do, and you have to sum it over the columns, or row. Xy means this can be written as x comma y, summation x comma y. That means through either you do it by the row or either you do it by column. So let's do it by row. Okay. So 1 by 6 whole square plus 2 by 6 whole square, 2 by 6 whole square plus 1 by 6 whole square. So that will give you energy. So this is the energy coming. Okay. This is the energy coming. Similarly, you can find the entropy. Entropy is given by this formula. So nrxy log nrxy. So nrxy is nothing but all the elements of it into log to base 2 nxy. Okay. So like 1 by 6 log base 2 1 by 6 plus 2 by 6 log base 2 2 by 6, 2 by 6 log base 2 2 by 6, and 1 by 6 log base 2 1 by 6. Okay. This you can do, and you can get your entropy. Okay. And minus of it, entropy is always minus, because entropy of a system is always increasing. Okay. That is why it is always written as minus. So that is why entropy is given by this formula. Okay. So this is the formula of entropy. Similarly, contrast you can calculate by this sigma xy x minus y square nr xy. So again here x minus y. Now x minus y, if we just do about the diagonal point, so x minus y is nothing but the index. Okay. So if we just focus the diagonal point, so this diagonal is 0 comma 0, and this diagonal is 1 comma 1. Okay. So that is why 0 minus 0 is 0, 1 minus 1 is 0. So this two, the contrast is 0, but this two will get some contrast. So that is why as the diagonal does not mean anything to us, so that is why we have given as 1 0 nr 0 1 and nr 1 0. So that is how you can calculate the contrast. Similarly, homogeneity can also be calculated by this nrxy 1 plus x minus 1. Okay. You can just calculate the homogeneity by this formula. Okay. Then correlation is given by actually this formula. Okay. Where is correlation? Yeah, correlation is given by this formula. Okay. Sigma x sigma y at the denominator, and this in the numerator. So how to calculate this? So first you have to calculate this f0 and f1. Okay. What is f0? F0 is nothing but the f0. Whenever we are talking about f is nothing but we are talking about rows. Okay. So you just have to take the row, you have to sum it for the first row, that is f0. Okay. Sum it for the second row, so that is f1. Similarly, g0 sum it for the first column, g1 is sum it for the second column. Okay. So this is f0 f1, g0 is g1, and then you have mu x, that is x into fx. Okay. So again x into fx. So just do this for mu x. Similarly, you can do the mu y. Similarly, you can get the sigma square x and sigma square y. Okay. Sigma x square and sigma y square. Similarly, with sigma x and sigma y is nothing but your variance. Okay. You have to get the standard deviation. Standard deviation is nothing but root over variance. So whatever variance you are getting, just do the root over of it, and after that you just apply this formula, and you apply this formula. This is numerator part, and denominator is nothing but sigma x sigma y, and you will get the correlation of this co-occurrence matrix. Okay. So this is the thing. So is this thing clear to all of you? Is this thing sorry. So is this thing clear to all of you? How to get a co-occurrence matrix and how to get a normalized co-occurrence matrix? At least this part, is it clear? Any doubt in this part at least? How to get a co-occurrence matrix and how to get a normalized co-occurrence matrix? Any doubt? Am I audible? Hello, am I audible? Hello? Am I audible? Am I audible? Guys, am I audible? Hello? No response. Am I audible, guys? Can anyone confirm? I think voice is going from my side. Am I audible, guys? Can anyone confirm? Hello? Am I audible? Can anyone please confirm? Voice is going from my side. Am I audible, guys? Hello, hello. Your voice is going from my side. Swati, can you confirm? Am I audible? Chandra or Sudhakar, can you confirm, please? Am I audible?
Yes, sir. Yes, sir.
Okay, nice. So is the co-occurrence matrix clear to all of you? Co-occurrence or normalized co-occurrence matrix? Any doubt in this? At least in this part, any doubt?
Sir,
Yeah.
solution of this problem, not only this, each and every problem solution is very lengthy, right? But in final exam, how it is possible? It will take more and more time to
No,
solve the problem.
you won't be given that long calculations, but at least if you are given a matrix like this, can you compute the co-occurrence matrix or a normalized co-occurrence matrix out of it? Can you at least do this part? If you can do this part, then others are just formulas. Okay, can you do this part? I think if you can do this part, if you understand this part, others are just like formula, direct formula. You just add up, like for energy you just add up, for this entropy you just do this element multiply by log 2 base of that element. So all these are very simple formulas. Okay, if you just understand this part, can you just compute a co-occurrence matrix and a normalized co-occurrence matrix if you are given an image matrix? Can you do that part? Just tell me. At least this part. Can you do it?
Yes, sir. Yes, sir.
Okay, you can do it, right? Then other part it is just normal formula. Okay, just you can, if you just, yeah, now it might be looking difficult to all of you because you are doing for the first time. Okay, but just write in the form of pen paper. It is actually not that tough. Okay, just try it in a pen paper. It is actually not that tough. And in exam, no need to fear, that long question won't come in exam. You should be given like that. If you are given a matrix, just calculate a co-occurrence matrix of it by just calculate a co-occurrence matrix or normalized co-occurrence matrix out of it. Okay, that part would only be given. So I hope that part it is clear to all of you. Okay, or you are given a formula like this is a formula for entropy, like that, this type of question. So I think you can do it. Okay, so this is the thing. So this is the thing. I hope others are just formula, so I'm not going. And then we have this something called texture energy feature. Okay, this is the fourth part of this uh, texture descriptor. Okay, so texture energy feature, it is proposed by laws 1980, so that is why it is sometimes called a law of texture energy feature. Okay, so basic idea: measure the local variant of intensity in an image to detect patterns like edge, spots, wave, ripple, etc. These features are particularly useful for texture classification and segmentation. Okay, so actually here what we are doing, we are like in the LBP, we are calculating the local binary point decimal value. Here we are calculating the energy. Okay, so this is the formula for energy. So just show you a question so it will be more clear. So this is the image, and then you are giving a mask. This is a horizontal mask. Okay, this is a mask. Any mask can be given to you, but here this mask is given to you, and then you are told to compute the texture energy using absolute sum. Okay, so absolute sum nothing, but this is actually the formula. So again, no need to see this part, but you are just asked to calculate the texture energy. How you will do it? So first you will do this. Okay, first you will take the center pixel. Okay, because first you will take the center pixel, that is I dash 2 is I dash 2 2. Okay, that is 30. Okay, this is the center pixel. Okay, and then you will just put the mask on it. As your mask is of the same size of your image, so there no need to worry about anything. Just put the whole mask on the image. How you can put the whole mask on an image? Just multiply your mask element to the image element. Okay, by this you can put the whole mask to the image. So minus 1 into 10, that will be your m dot I, then minus 20, then minus 10, then all the middle will be 0, then 10, 20 and 10. This will be your m dot I or I dot m. Okay, this will be I dot m. But then what you have to do here, you have to do the summation of all the intensity values. So summation, it can be very well done. First is coming minus 10 minus 10 plus 20 minus 10 minus 20 minus 10, so that is minus 40. And second row is 0 0 0, and third row is 10 20 and 10, that means 40. So this is giving us minus 40. This row summation is giving us minus 40, this row giving us 0, and this row giving us 40. So just find out the sum. So minus 40 plus 0 plus 40, that is 0, and do the absolute sum of it, that means this. So that is giving us 0. Okay, and 0 and divided by, you have to do it by number of elements, that is n square. Okay, n square, that is the number of element, that is already given, 3 cross 3, that is 9. So 0 divided by 9, that 0 is your texture energy. Okay, as here the middle portion is giving 0 0 0, and your sum adds up, so that is why energy is coming 0. Otherwise the energy might also not come 0. Okay, if your values are different, energy might also not come 0. So that is how you can find the energy in your texture energy feature. Okay, so is this thing clear to all of you? What you have to do, you have to just multiply the image matrix to your mask matrix element wise. Okay, not the actual multiplication, but the element wise multiplication you have to do. Then you have to take the sum of all the elements, and then you have to divide by number of elements. Okay, so by that you can get the energy of your energy. Okay, energy for a given mask of an image. So is this thing clear to all of you? Very simple. Image into mask element wise, and then do the summation of all the elements divided by number of elements. So by that you can get the energy. So is this thing clear to all of you? Clear, right? Any doubt in this? Okay, no doubt. Okay. Now this was the last texture description, and then there is some comparison of texture description you can see. Okay, and then we have this last image descriptor. Image descriptor, numerical representation of visual content on an image. So actually image descriptor means we are talking about global image descriptor. So it is a feature vector that represents the entire image as a whole rather than individual parts of the local region. Okay, so entire image. First patch, we have been talking about patch, then we are talking about description. Now we are talking about the entire image. So for this we have these two methods. One is this bag of visual words. Okay, bovw. Okay, you can read what first they do the feature detection, then it creates a visual vocabulary code, assign descriptor to this visual words, and then build a histogram. So actually this is the summation of this both your patch detector as well as your texture detector. Okay, so this is the image detector. Similarly, VLAD, it is an improved version of your bag of visual word. You can read all this. Okay, everything is here. So you can read all this here. Also in creating a visual vocabulary, what we are doing, we are using this k-means clustering. Okay, so k-means clustering is important. Again, all these theories are available. I am not pondering much, and this is the this I have given the comparison of global descriptor bovw and vlad. Okay, and this is the application. You can see by this image global descriptor you can do the query of image. Okay, content based image retrieval, image search based on visual content. Okay, so this you can do. Now we will be quickly moving on to the question. This is our first question. Which of the following is a true for SIFT and SIRF? Computation of scale space of histogram gradient directions are approximated in SIRF compared to SIFT. Okay. Second is integral of images are used in SIRF to speed up computation. C. Small Gaussian used in SIFT are approximated by box filter in SIRF. D. Haar wavelet response are used to accumulate the orientation in SIFT and SIRF descriptor. So any guesses for this? Any guesses for this? What is the correct answer for this? Any guesses? So let me remind you, SIFT and SIRF, right? SIRF is an extended form of SIFT. Okay, SIRF we are doing approximation, so first option is right. Second, we are doing integral of images to speed up computation, that is also right. C, that is we are approximating Gaussians with the help of this box filter. So C is also right. Haar wavelet is actually used in SIRF, not in SIFT. Okay, so option D is false. So option A is right because we are doing approximation. Option B is right. We are doing this integral of images to speed up the computation. Option C is also right because we are using box filter for this approximation. Option D, this Haar wavelet response, okay, it is used in SIRF, not in SIFT. So that is why option D is incorrect. Okay, so option A as well as option B as well as option C is right. Option D is wrong. Okay, option A as well as option B as well as option C is right. Option D is wrong. Let's move on this to this next question. This is actually should I discuss? Let's just leave it because this is actually okay. Let's just discuss which of the following is true. Ransack are best suited for fitting outlier. So yeah, ransack, it is known as random sample consensus. It is actually, it works well, robust against outlier, but it is not used for fitting outlier. So that is why it is false. Then how transform, it is best suited for line fitting in the presence of many line. So yeah, how transform maps point in Cartesian space for this parameter rho theta. Again, this all these things are not related to this, but here it is given here, so just I am discussing. Then this Kullback-Leibler divergence, it is best suited to find optimal parameters when points belonging to the line are given. So it is false actually. The scale divergence, it is a measure of dissimilarity between probability distribution, and it is not used in fitting. Okay, so this is not used in fitting. Okay, best suited to optimal line parameter, it is not actually used in fitting. Okay, so that is why this is false. About these things we will actually read in the next week, so that is why no need to worry about this question. Okay, and third, D, option D, average case time in complexity NN using KD tree is given by this, where D is the dimension of the feature space. So actually this KD tree, it always do this log complexity, so this is the formula of log complexity. So option D is right. So no need to worry about this question, so I am leaving this as of now. This is important. Consider a set of parametric equation, this x, y representing a 2D curve. Compute the tangent vector at t equals to 2. So can you do this? Compute the tangent vector. Can you do this? Any guesses how to do this? What is tangent? Tangent is nothing but the derivative of the function. Okay, so tangent at x comma y, it is given by del x comma del x by del x comma del y. Okay, del x here, as it is parametric with respect to t, so your tangent will be given by del x by del t and del y by del t. So very simple, del x by del t means just differentiate the function and put the parametric value. Similarly, del y by del t, just differentiate the function and put the parametric value t equals to 2. So x equals to t cube plus 2t square. So what is del x by del t? It is 3t square plus 4t. Similarly, what is del y by del t? It is 2t plus 1. Okay. So let me show you. So very easy. Just compute this del x by del t or x dash t, that will be equal to 3t square plus 4t. Here y dash or del y by del t, that is equal to 2t plus 1. Okay. So this is given. And then to compute the tangent at t equals to 2, it is very easy. Just put t equals to 2 here. So 3 into 4, that is 12, plus 4 into 2 is 8. Okay, 12 plus 8, that is 20. And then 2 equals 2 into 2, that is 4. 4 plus 1 is 5. So 20 comma 5 is your answer. So option C is your answer. So is this thing clear to all of you? How have I solved it? I think it is clear to all of you. Can you confirm it is clear or not? Clear, right?
Sir,
Yeah, please. Yes, please.
yes, sir. Understood.
Yeah, yes. It's just del x by del t, del y by del t at t equals to 2 to get the tangent. Okay, it is very easy.
Given equation, we have to derivate. After that, we have to substitute t value, right?
Yeah. Just get the del x by del t and del y by del t, or x dash or y dash, and then put t equals to 2. Okay, and you will get the answer. Okay. So this is the third question. Question number 4. Consider the following matrix: 4 sample data points, 1, 2, 2, 1, 3, 2, 2, 3, and this is this is given like this. Okay, compute the covariance matrix using data point x. Okay, this all the 4 point is given by this matrix. Okay, 1 2, you can see 1 2 2 1 3 2 and 2 3. So compute the covariance matrix using data point x. Okay, so how to get the covariance matrix? So first step is to get the mu. Okay, first step is to get the mu x and mu y. Okay, mu x, how you can find? 1 2 3 2. So x direction. Okay, this is the x direction. So mu x you can find by this. So 1 plus 2 plus 3 plus 2 divided by 4, because 4 number of elements are there. Similarly, mu y, you can get the mu y, that is mu y, that is, or you can say from this it is more clear. So x is 1 plus 2 plus 3 plus 2 divided by 4, that is mu x. Okay, similarly mu y is 2 plus 1 plus 2 plus 3 divided by 4. So mu x and mu y, or the mean, that is calculated by this. So mean is coming to mean x is coming to, okay, and mean y is also coming to. So this is the mean vector. Okay, and then what you have to do, you have to subtract the mean vector from the mean vector to get the center point. Okay, so center point, how you can get? Xc is x minus mu. Okay, so x minus mu, but you have to do x minus mu in x direction. Here you have to do x minus mu x, and here you have to do x minus mu y. As mu y and mu x both are equal, so just subtract by your mu vector. Okay, so by this you can get the center the data, or you can center the data or get the xc matrix. And once you got the xc matrix, you have to calculate this, that is calculate the covariance matrix. Covariance matrix is given by 1 by n xc, that is the center transpose of the center matrix into the center matrix. So you have the center matrix, you just multiply this and you will be getting the xct and xc or transpose of your center matrix into the center matrix, and then divided by number of elements or number of points. Okay, number of points is 4. Okay, so 1 by 4 you do, and you will be getting the covariance matrix. So your covariance matrix is coming 0.50, 0.50, 0.5. Okay, So this is what your covariance matrix come. So let me again remind you the step. First you calculate mu x, you calculate mu y, and then you just center the data. How you center the data? You do x minus mu. This mu is a combination of mu x and mu y. So here you just put mu x, okay, here mu x, x minus mu x, okay, and here here you mu y, okay, mu y. So this is x minus mu x, and this is y minus mu y. X minus mu x, y minus mu y. By this you are getting the center matrix, okay, or you are centering the data. Once you have centered the data, you have to apply this formula. That is 1 by n. N is the number of element. Transpose of the center matrix into the center matrix. Okay. By this you are getting the answer. Okay. So this is the answer. 0.5, 0, 5. So option B is the right answer. Okay. So is this thing clear to all of you? Is this thing clear?
Sir, where is 1 by n?
1 by n, this 1 by 4, last step, 1 by 4. N is the number of points. 4 sample points are given. So that is why 1, 2, 2, 1, 3, 2, 2, 3. 4 sample points are given. So that is why n equals to 4. Okay?
N value how to calculate? N.
N
Value.
value, no? N is the number of points.
Number of points.
You are asking n, no? N is the number of points. So 4 sample points are given. So that is why n equals to 4.
Equal to 4. Okay, sir.
Okay. You got xc, right? How to calculate xc? Or the center matrix? Yeah. So that is important. Okay. So this is the thing. Next, the top left corner of the matrix is considered as 1, 1 and the indices increment for x, y axis along the horizontal right vertical direction. So this is actually the A matrix. Compute the magnitude and orientation in degree using the first order difference operator at the center pixel. Center pixel is nothing but 0.2. Okay, so first order difference operator, you have to calculate the magnitude as well as orientation of it. That means you have to calculate Ix or Ix, Iy. Similarly, you have to calculate orientation, that is theta. Ix, Iy, this can also be called as Gx, Gy, okay? And then you have to calculate theta. So Ix, what is the formula for Ix? Ix is equals to, very easy, this is the formula. Ix or Gx, whatever you tell, same thing. So where we have calculated it. Yeah, this is the thing, okay? This is the thing. So this too you have to calculate it. Sorry, this whole thing you have to calculate it. Okay, so first you have to get Ix, or you can say Gx, and then Gy, and then you have to calculate the magnitude. Similarly, you have to calculate the direction. So what is Ix or Gx? That will be equal to Ix plus 1 y minus Ix minus 1 y, Gy Ix y plus 1 I minus Ix y minus 1. Okay, so by that you can calculate this. So let's move on to the question again. Yeah, so very easy. So what is Ix? Ix is Ix plus 1 minus Ix plus 1 y minus Ix minus 1 y. So what is Ix x plus 1 y? That is 0.5. Ix minus 1 y, that is 0.3. So your Ix or Gx will be 0.2. Okay. Similarly, what is Iy? Iy is 0.1 minus 0.3. Okay. 0.1 minus 0.3 minus 0.1. Okay, so let me again tell this. Gx or Ix is 0.3 minus 0.5, that is minus 0.2, and this is 0.3 minus 0.1, that is 0.2. Okay, and then you can calculate the magnitude, that will be root over minus 0.2 square plus 0.2 square, and your direction will be tan inverse 0.2 by minus 0.2. Okay, so that is the thing. So let me show you how to do it. This is your Gx, okay, and this is your Gy, okay. So this is Gx and Gy, and you can easily compute it. Okay, gx and gy. So this is ix plus 1y, this is ix minus 1y, and you can calculate the gx. Similarly, you can calculate the gy, and easy, magnitude is easy, that is this, that is coming at this that is coming at 0.1414, and then you can calculate the theta, that is arc tan inverse gy by gx. Okay, so that is how you can do it. Okay, very easy, that is how you can do it. Okay, so this is the thing. So is this clear to all of you?
Sir, here Gx equal to I of x plus 1 comma y, right?
Yeah.
X means
X
x
means
not
X means center pixel, right? Means the target pixel. Target pixel, here it has been given where center, yeah, center pixel, right? Center pixel is your target pixel, right? So xy is your target pixel. So target pixel is center pixel. Center pixel means 2, 2. Okay, so xy is 2, 2. Okay.
okay. Okay.
So xy
So
is 2, so 2. So 2 plus 1 comma y. So 2 plus 1 is 3, 2. So 3, 2 is 0.3. Okay. Similarly, x minus 1 comma y, that means 1, 2. So 1, 2 is this 0.1. So 0.3 minus 0.1 divided by 2. Okay. So you can get it minus 0.1. Okay. Sorry, 0.1 minus 0.3 divided by 2. Okay. So this, yeah, 0.1 minus sorry, x plus 1. Okay, x plus 1. X, oh sorry, this is y. Okay, x is this. Okay, x plus 1, x is this direction, horizontal direction. So x plus 1, and this is x minus 1. Okay, so minus the 0.3 minus 0.5. Similarly, y y plus 1, this is this, x y minus 1 is this. So 0.3 minus 0.1 divided by 2. Okay, so this is x direction and this is y direction. Okay, so this is the, so this is the and once you get gx and gy, it is very easy. Just do the magnitude is this, and orientation is this. Okay, so orientation is minus 45 degrees coming. Okay, so this is the, so is it clear? Clear, right? Okay, let's move on to the next question. If an octave in SIFT operator has 10 images, then the scale factor by which each image in octave differs from next image is, so how to do it? So this is the formula. Actually, if an octave has 10 images, then s plus 1 will be equal to 10. Okay, s plus 1 will be equal to 10, and you have to calculate the s. And then how you can get the scale factor? Scale factor is nothing but 2 to the power 1 by s. Okay, so s, you can just calculate s. S is nothing but 10 minus 1. Okay, that is 9, and once you get the scale, it is very easy. K will be 2 to the power 1 by 9. 2 to the power 1 by 9 is coming, is coming, okay, is coming 2 to the power 1 by 9 is, it is coming actually this. Okay, 1 point it is coming actually this 1.80 1.0800. Okay, so this is the thing. Okay, so this is how you can calculate it. So just from s, you have been given s, you have been given s plus 1. S plus 1 is the number of image that has been given in the octave. Okay, so s plus 1, you have s plus 1. From s plus 1 you calculate the s. Once you get the s, k value is nothing but 2 to the power 1 by s. So 2 to the power 1 by 9, that is coming 1.08. Okay, just do 2 to the power 1 by 9 and you will be getting this 1.08. Okay, so 1.080, option A is your answer. So is it clear? Very easy. S plus 1 will be your number of image in your this SIFT operator, and to get the scale factor, nothing, you have to do k equals to 2 to the power 1 by s. Okay, just do this and you will be getting the answer. So this is very simple. Okay, just do this. 2 to the power 1 by 9, you just do this, you just forget this thing, you just do this, and you will be getting the answer. Okay. And then next thing, given two feature, we are given two feature f and g. Okay, compute L1 and L2 norms between f and g. So L1 and L2 norms, L1 is given by, yeah, you have f, you have g, you have this f minus g. Okay, just get the f minus g. F minus g is this, and for L1 norm, this is the formula of this L1 norm, and you just what you do, you just do the mod of each difference. Okay, so mod of -3, mod of 1, mod of -4, mod of 1, mod of 0, and like this, mod of 1. And L1 is coming 10. Okay, L1 is coming 10, and L2 is nothing but root over this, or to the power 1 by 2. Okay, so just do fi minus gi whole square. Okay, just do fi minus gi. F minus g is already given, just you do the fi minus gi. Okay, just do the fi minus gi. Fi minus g, f minus g is already given, just do the fi minus gi square. Okay, so fi minus gi is given -3, so fi minus gi square will be -3 square. Similarly, this will be 1 square, this will be -4 square, this will be 1 square, like that. Okay, so by this you can get the L2. Okay, so once you root 28 is coming, that is 5.29. So your answer is C. So this is your L1 operator formula, this is your L2 operator formula. Okay, and in practice, your LP, any LP operator, it is given by fi minus gi, fi minus gi, fi minus gi, fi minus gi mod of p, and root over 1 by p. Okay, 1 by p. Okay, so p equals to 1 for L1 normalization, p equals to 2 for L2 normalization. Okay, so just you can find the L1 and L2 norm by this. So again, it is a very simple question, so I hope it is clear to all of you, right? So this is very important actually, L1 and L2, so it might come in your assignment. Okay, so this is the thing. Which of the following is that true for edge and corner? A corner will have low maximal and minimal curvature. A corner will have high maximal and minimal curvature. An edge will have low maximal but very high minimal curvature. An edge will have high maximal curvature but very low minimal curvature. So any guesses for this? What about corner and what about edge? Corner, it is very easy, right? A corner will have high maximal and minimal curvature, means both the lambda values are actually large. Okay, but in case of edge, lambda plus is large but lambda minus is small. Okay, so an edge will have high maximal curvature but very low minimal curvature. Okay, so option B as well as option D is right. Okay, so this is the thing, option B as well as option D. So this is the thing, an edge will have high maximal and but very low minimal curvature, means lambda plus is large, lambda minus is small. Okay, so this is the thing. Now given two feature, each this and this, again this are given, LP normalization if p equals to 3, then again you have to do the f minus g first, and then you have to get the LP formula. This is LP formula, just do this, and then what you have to do, you have to compute this thing. Okay, so just first all the things calculated, all the f minus g calculated, just make cube of this, -4q, 0q, -1q, 2q, and -1q, and then just sum everything, and then do the 1 by 3 of it. Okay, so it is coming 4.20. This is actually integer type question, I think. Yeah, that means value type question, so 4.20 is coming. So this is the thing. So this LP normalization, it is clear. Is it clear to all of you? Is it clear?
Yes, sir. Yes, sir.
Okay, nice.
Just part, right? We have to substitute values.
Yeah. Fi minus gi can be calculated by subtraction. Next step, what you have to do, you have to whatever p value is there, either p is 2, you have to do the square of it. If p is 3, you have to do the cube of every f minus gi. Okay, means every element of f minus g. okay, and then you have to do the absolute sum of everything, okay, and then do the 1 by p root, okay, 1 by p. Here is as p is 3, that is why 1 by 3 root, okay. So just do 74 1 by 3, so your answer is coming 4.20, okay. So this is the thing. This is very important actually, LP normalization, because if you know LP normalization, you can calculate both your L1 normalization as well as L2 normalization by putting p equals to 1 and 2. And find the eigenvalue of the matrix 1, 2, 2, 1. Again, it is very simple. What we have to do? We have to do this 1 minus lambda, 1 minus lambda minus 4. Okay, so lambda is lambda minus 1 whole square minus 4 equals to 0, and you will get the lambda values. So very easy. It is nothing but a minus lambda I, a minus lambda I mod a minus lambda I mod will be equal to 0. So now it is very easy. A minus lambda I, just do the determinant of a minus lambda I. Okay, so a minus lambda I, lambda will be subtracted only on the diagonal, because your I is nothing but, sorry, I is nothing but 1 0 1 0 0 1. Okay, sorry, this 1 1 1 1 0 0 1 1 0 0 1 0 0 1. Okay, 1, this is 1, this is 0, this is 0, and this is 1. This is your I. Okay, so that is why only we subtract diagonal, because this true value will be 0, so lambda into 0 is nothing, so that is why we don't subtract lambda from this, we subtract lambda from this. 1 minus lambda, 1 minus lambda minus 4. Okay, 1 minus lambda square minus 4 equal to 0, that will be your characteristic equation. And then very simple, you can do either factorize it, or you can just do the minus b plus minus root over b square minus 4ac by 2a, and by that you can get the two values of lambda 1 as well as lambda 2. It is coming 3 comma minus 1, so option C is right. Okay, so option C is right. So I hope it is clear how to get the eigenvalues. Clear, right?
The last, that is formula,
Yeah.
or lambda equal to 2 plus or minus under root 4 plus 12 by 2.
Yeah. So ax square plus bx plus c equals to 0. This is nothing but, this is a equation of a quadratic equation. Okay, so this is quadratic equation, ax square, this is a, okay, ax square plus bx plus c equals to 0, quadratic equation. The roots are given by x equals to minus b
Plus or minus
plus minus root over b square minus 4ac. Okay, b square minus 4ac, 4ac. Okay, a into c, okay, ac, 4ac, everything is in this root over, and then divided by 2a.
b square minus 4ac, right?
Root over b square minus 4ac minus b plus minus root over b square minus 4ac divided by 2a. Okay, so what is b for, yeah, so let's see here. What is a is 1, b is minus 2, c is minus 3. Okay, so minus b means 2, that is why 2, root over b square is minus 2 square, that is 4, minus 4ac, minus 4 into a is 1 and c is minus 3, so that is why plus 12 by 2a, 2 into 1, a is 1, so that is why 2a. So 2 plus minus 4 by 2, either you will have 2 plus 4 by 2, that is 6 by 2, that is 3, or 2 minus 4 by 2, that is minus 2 by 2, that is minus 1. So that is why option C is right. Okay, minus b plus minus root over b square minus 4ac by 2a. Okay, clear, right?
Clear, sir.
Okay, so by this I am ending the session for today. The theory and all I will be giving you the slides, so please just look at the theory. This theory question might come, what is the SIFT, what is this, what is SURF, etc., comparison, some features, etc. So that is why please look in all these descriptors. So this slide will be given to you, just look on all the theory part, and numerical, all the numerical. I hope I have solved all the numerical, okay, associated with this week. So by this I am ending the session for today. We will meet on the next Friday, same time, 6 to 8 p.m. Okay.
Thank you, sir.
Okay. Bye.